so for those of you that started, this is integration by parts. So what did you let be your u? ln(t). What did you pick to be dv then? T to the 1/2.
I didn't write it that way, but yeah.
It doesn't matter if your order's a little bit different, as long as you chose that to be that, that's okay. Derivative of natural log t is
Over t dt.
1 over t dt. And the antiderivative of t to the 1/2 is
2/3 t to the 3/2.
2/3 t to the 3/2. We have to institute a pause rule for Devin here. It's all good. Is that okay with everybody? You got that? Okay. So the formula is this equals uv minus integral v du. So 2/3 t to the 3/2 ln t minus 2/3 integral 1 over t times t to the 3/2. Yeah, dt. Those d thingies will matter a lot in Calc 3 because you're going to have dx, dy, dz, and the order that they appear determines the order in which you do stuff. So it also matters for substitution, doesn't it? Like you kind of replace that dt with some things that involve other variables sometimes, right? Okay, so what does the stuff inside that integrand cancel to? T to the 1/2. There is kind of an obvious pattern that's happening with these natural log things, isn't it? Like when you do this cancellation, you kind of get back to the thing you had originally. You see what I mean? And that's because you were multiplying its antiderivative by 1 over t, which takes away 1 from the power. Which undoes what you just did, right? All right, so 2/3 t to the 3/2 ln t. And then the antiderivative of t to the 1/2 is 2/3 t to the 3/2. So can I just go ahead and say 4/9? Okay. And then don't forget your plus c.
But why would you want to do that? If you left it 2/3 t to the 3/2, you could factor it out.
You could do that too. It doesn't matter. I mean, like, you can factor stuff out, you can leave it distributed. I don't have a preference as to what way you do it. I think on the first take-home quiz, I did say you had to distribute, like as in leave things distributed. And the reason for that is that if I didn't say that, I had students who were leaving multiple sets of nested parentheses, and it wasn't clear that they could actually distribute negatives correctly. Does that make sense? Okay. So I think in general, just leave it like this. Unless I ask for it to be factored, you don't have to factor it. WebAssign is smart enough, it'll take either answer. At least it should be. Okay. This next thing is actually kind of review. So this is what we're going to do today. We are going to take some integrals that involve trig functions, and we're going to make it so that we can integrate them using a substitution of some sort, by manipulating the trig using identities. So can you do this problem just using basic substitution?
Yeah.
Yes. What would you let u equal? Sine x. No need to use dw here because we only have to do 1, right? And the reason that you do that is because what this really is it's sine of x to the 5th, right? That's what that like little 5 means, right? And so the sine is inside this 5th power function, right? Okay, so what's the derivative of that sine then?
Cosine.
Cosine. That's cosine x dx. So the cosine x dx is replaced by du, and the sine is replaced by u, and this integral becomes integral u to the 5th du. It's like a baby integral, right? Okay, so what's the antiderivative of u to the 5th? 1/6 u to the 6th. So can I just put in what u is? So 1/6 sine to the 6th x plus c, because that really is 1/6 u to the 6th plus c. I'm totally cool if you combine those steps, like both anti-differentiate and put your substitution back in. It's just, otherwise it's extra writing and, you know, laziness wins out, right? Always. How about the next one? So how about this one? What are you going to substitute? Tan x. And the reason you chose that is because the derivative of tangent appears there, right? So u is tan x. The derivative of tangent is secant squared x. And so when you make that substitution, this becomes
u to the 7th.
another baby integral, right? Easy one. So the antiderivative is plus c, or 1/8 tan to the 8th. So that should have been stuff that you already know. If you tell me your name, I'll sign you in. Yeah, what's your last name? It starts with an L?
Yeah.
Oh, yep, okay, got it. All right. Okay.
So this class starts at 10:30 and not 10:45?
Yes, and I think I explained only briefly, and I think I just saw Zach Meredith, right? Yeah, it's you. Okay, you didn't sign in, but I gotcha. Okay. You did not, but it's all good. Oh no, that was somebody else who didn't sign in. Crap. Scroll that out.
I guess they're here.
No, that was my initials. I can undo what I just did. Okay, so the basic crux of what we're going to do today is we're going to take integrals of combinations of trig functions, and we're going to make them so they're like the ones we just did. As in, you're going to mess with the trig so that making a u-substitution works. And to do this, you're going to need to know some trig identities. There are only 6 that you have to memorize, and this is 3 of them. Okay? This is half. And there is a really, really, really easy way to derive the second 2 from the first one. So first of all, this first one, there's a reason they're called the Pythagorean identities. Why do you think that is? There's this guy named Pythagoras with this theorem that says a squared plus b squared is c squared, right? So if you're looking at the unit circle, what is the length of a hypotenuse of any triangle in that unit circle? 1. Like specifically that c is 1. And didn't you learn that this distance is the cosine of your angle, right? This distance is the sine of said angle as well, right? So therefore, okay, by Pythagoras, bam, okay? That's why that one is what it is. And now how you get the others is by clever division. 1 over what trig function makes secant? 1 over cosine, good. You had a good algebra 2 teacher who taught you that. 1 over cosine, that of course was me. So that makes this into sine squared x over cosine squared x plus cosine squared x over cosine squared x equals 1 over cosine squared x. And you see how that actually is a second identity? Sine over cosine is tangent, cosine over cosine is 1, right? I don't actually have these memorized. I just remember how to get them. I have to like rederive them every time. So, but how would you get the last one? What do you divide by? No. You divide by sine squared. You ask how to make cosecant squared.
Oh, you mean, I thought you were going from the 2nd to 3rd.
Oh, well, you probably could. Actually, no, that probably will work. Yeah, that will work.
That's what you were talking
Nope.
about.
It will work, but I think it's easier to go from this one to that one by dividing by sine squared. But you're right, dividing by tangent squared will also actually do it. It's just simplifying cosecant squared over tangent squared is not as nice as just saying, oh, 1 over sine squared is cosecant squared. So you do have to know those, but I think if the first one is pretty obvious to memorize, right? You just know how to get the others. It's not that bad, right? Okay. So here's the most basic one. Sine cubed of x. Did you ever say sine cubed? Okay, great. Because I kind of modified my notes and I just need to make sure I didn't like not update them. So if the problem up here doesn't match what you have, let me know. Okay, so why can't I let u equal sine? What's the problem with that? There's no cosine to be the du, right? So you got to fuss with it. And what you do is you break this up into sine squared x times sine x. And this sign is going to be saved to be part of the du that's in your substitution. So if your du is going to be sine, what's your substitution probably going to be? This is going to be your du part of it, eventually. It would work if these were cosines, right? Can you change those into cosines? Yeah, how? It'd be 1 minus cosine squared. And you see that after that manipulation, you can actually do a substitution? Yeah. So then you can let u equal cosine of x, and du is negative sine x dx. So you plug in negative du for sine x dx. So I'll stick that negative out in the front, integral 1 minus u squared du. A fairly common mistake, so is the substitution okay? Okay, and you only can make that change if you have an even power on the sign, right? That formula is for sine squared, right? Okay, so it is easy. I see students make the mistake of losing that negative sign quite a bit. So I'm going to actually distribute it through, just so it's taken care of. And that's going to change this into u squared minus 1, right? Okay. And now it's a baby integral again, right? What's the antiderivative of u squared? 1/3 So can I say 1/3 cosine cubed x, just to do the antiderivative and plug it in at the same time? And then minus, what's the antiderivative of 1? U, so u would be cosine x. You should be careful that you say u and not x. Does that make sense? Plus c. That class is way more fun than I am. Okay. Does everyone understand kind of how that worked? Yes. So the typical pattern there is if you have an odd power on a sine or a cosine, you save one of those to be the du and change the others into the opposite variable. Does that make sense? Okay. So something must be saved to be your du. Okay, let's try that. So which one can you pull something off of and save it?
The sine squared x.
Okay, if you pull off a sine squared x, don't write this down because it's not going to work, okay? You're going to get cosine cubed x, a single sine x, and another single sine x. Do you have a formula to change that single sine into something else?
No.
You got formulas for squares, okay? So that method ain't going to work. Pull off a single cosine, so we'll have cosine squared x, sine squared x, save a single cosine. So that's saved to be your du. Say that again? Is what just one?
No, because you'd have to add cosine squared and sine squared to make 1.
Yeah. Okay, I think I see the question now. Yeah, cosine squared plus sine squared is 1, but not times. Yes?
Would a good rule for these be like you always want to choose the one that's got to an odd power?
Yeah. And if they both have an odd power, you can go either way. Yep. So the good rule of thumb is that whichever has an odd power is the one that you're going to pull one off of and save and then change the rest. That is a good rule of thumb for sine and cosine. It's different for tangent. And if both powers were odd, you could actually do it either way. And I try to not, there's an example where we'll do one problem both ways to show you that it is possible. So what does cosine squared change into then? 1 minus sine squared. And then your u will be sine x. And your du will be cosine x dx, right? So this becomes the integral of 1 minus u squared times u squared du. And there does not exist a product rule for antiderivatives. Yeah.
I just wanted to ask why we chose the cosine to turn into the weird thing.
Because if we changed the sign, then our substitution would have had to be cosine. And if you let u be cosine, du is sine, right? That's not what we have. Does that make sense?
Just trying to make it clear there.
Yep. So now what do you do next? Distribute. Integral u squared minus u to the fourth. Everybody say the answer with u's loudly as we can bother the class next to us. What's the antiderivative of u squared minus u to the fourth? Ready, set, go. 1/3 u to the third minus 1/5 u to the fifth plus c. Sorry. Yeah. Woo! Okay, you can go get the message. 1/3 sine cubed x minus 1/5 sine to the fifth x plus c.
Revenge is sweet.
That was awesome. Great, thanks guys. So yeah, I think a good point. Sorry, I don't remember your name quite yet, so it's you. Yeah, sorry.
No, sorry, Desmond.
So Desmond had a good question. It was kind of like saying, well, how do I know what to change? You'll want the thing you're substituting to be the other trig function of what you've saved. Does that kind of answer your question? Somebody else had a question over here. Yeah.
So in the previous problem, you skipped that step? Or you said
You can still skip that step.
skip on the take-home quizzes?
Oh, totally, yeah. But definitely show this step, right? Like show what your substitution is, but if you want to both integrate and plug in what your u was, totally fine. Yep. Alrighty. So now you'll also will need these half angle identities, and this is for when you only have even powers. So for example, suppose I just asked you to find the antiderivative of cosine squared x. Does changing that into 1 minus sine squared x help you at all? No. Does breaking it into cosine of x times cosine of x help you at all? No. Okay, so
Well, wait. You could then break that into the integral of cosine x plus the integral of cosine x again, right?
I can just change multiplication into addition?
No, that's not what that would do.
So you're saying I can take this?
I thought there was a rule where if you had... No, I'm thinking of three.
You're thinking of derivatives. Yep, exactly. So there is no rule for products. None. You could actually, it is possible to do that by parts. And you use an around the world trick. Okay, I think when I learned this, that's the way I learned it. But this way is by far easier. Okay? So, but around the world will work. It's possible. If you want to do that, you can give it a try just for kicks. But the easier thing is to use one of these identities. And the thing, I realized that in pre-calculus, you saw them a different ways. Let me show you one of those. So how you saw it in pre-calculus probably was like this. 2 sine x is 1 minus cosine 2x. 2 sine x squared minus 1 equals negative cosine 2x. You probably saw it as cosine 2x is 1 minus 2. You probably saw it like that. If you ever saw it at all. I mean, maybe you did, maybe you didn't, okay? I don't know. I didn't teach you pre-calculus. Well, a few of you had, but if you were in my class, I made sure you saw that. You're lucky, the 3 of you in this here who were in that class. So the point is that doing this identity, you see how that changes the squared into no longer having a squared at all? And can you integrate like cosine 2x? Yeah. And the other thing to notice is that there's a pretty easy pattern there, isn't there? They're almost the exact same, right? Except for the one that changes sines into cosines is negative. Okay, so there's 5 out of 6 formulas you must memorize for trig. Okay, you only have one more.
So people on the tests ever get those backwards?
Of course, but then you lose like a point out of 6 or something like that. It's not a very big penalty. But I always think the cosine becoming cosine stays positive. So the thing to do here is change this cosine squared into 1/2 times 1 minus, it is pi over 3, thank you. Cosine of 2x. And you can choose to distribute that 1/2. Oh, and it should be plus. I was just testing you. Look at, somebody caught that, right? Because cosine. Yeah, okay. All right, so I'm just going to take the 1/2 out for now. What's the antiderivative of 1? X. And then how about the antiderivative of cosine of 2x? 1/2 sine 2x, or sine 2x over 2, same thing. And you're going to evaluate from 0 to pi thirds. And that's so, just knowing that identity makes it not very difficult, right? So that's going to be 1/2 times pi thirds plus 1/2 sine of 2 pi thirds minus 1/2 times 0 plus 1/2 sine of 0. Yeah, the pi thirds goes in for both x's, right? Yes?
I may be mistaken, but when we go from cosine to sine, would there be a negative?
It's the antiderivative.
Okay.
So here's how I figure this out, okay? I know that if I go this way, it's by taking a derivative, right? The derivative of sine is cosine. Does that make sense? So check with the sign error by doing the derivative.
All right.
No problem. Okay. So I am incapable of figuring out what trig things are without drawing myself a unit circle. So 2 pi thirds, this is single pi thirds here, right?
Yes.
And this is 2 pi thirds over here. And in that triangle, the base is 1/2 and the height
Just root 3 over 2.
is root 3 over 2. Okay? So the triangle is pretty much symmetric over there except for the x is negative, yes? So in that case, the sine of 2 pi thirds is also root 3 over 2. So 1/2 times root 3 over 2. So that would be, and then also sine of 0, 0. Okay. So you got pi 6 plus root 3 over how much? Almost 8, because of the 1/2 out in front. WebAssign wants exact answers, which means it wants dat. Okay.
Wait, but sine 2x,
Yeah, and so since x was pi thirds, 2 times pi thirds is 2 pi
sorry.
thirds, right? No, it's
Yeah.
all good. No, I make mistakes. It's good to check. I mean, if I seem wrong, you should ask. And about half the time I'll be wrong, so it's good to check. Yes?
Okay, I know, like, this doesn't technically need a calculator, but, if we happen to be using one, should we keep it in radian mode?
Yes. Definitely. You should keep it in radian mode. If you're given radians, keep it in radian mode. You're probably almost never going to use degrees in this class. And you should also make sure if you use a calculator that you don't stop thinking. Like, make yourself do it first, and then check with your calculator, because a lot of the time you push a button and your brain turns off. So, okay, next one.
is it
And
okay
you're-
if I only use the calculator when I see like just long computational 4-function math that I just don't feel like doing?
Sure. As long as it's not your take-home quiz, you're supposed to show your work, so, yeah.
Alright.
So sine to the fourth. So can I like take off a sine and change the sine cubed into something easy peasy? What are you gonna use?
You take 2 sine squares.
But that's squared. And then you'd have like, if you took off sine squared, you have the other sine squared.
But then you can turn it into the other one.
That's what you do. So I think some of you are already getting there. You take this and make it into sine squared times sine squared. And you replace each of them with their half angles. As in, this becomes the integral of 1/2 1 minus cosine of 2x. Can I just say the quantity squared? The whole thing squared? Because it's that thing times itself, right? Okay. We'll have to use the reverse chain rule when we're dealing with this. And it's going to be a little more complicated, but the basic idea is you use these half-angle identities. So let's simplify a teensy bit. What is 1/2 squared? 1/4. So let's pull that 1/4 out in front. if you expand 1 minus cosine of 2x times 1 minus cosine of 2x, what is that? 1 minus, how many cosines 2x? I just couldn't hear. 2, okay, good. 2 cosine 2x plus cosine squared of 2x. Okay.
That'd be another half angle identity.
It would be, good job. So does everybody understand that the first term you can integrate, right? The second term you can integrate. That third one, grrr. Okay, so what you have to do is you have to do a half angle again. And now let me write down what that cosine thing says with a different letter. So it says that cosine squared of w is 1/2 1 plus cosine of 2w. That's what the formula says with w instead of x, right?
Why are we doing that?
You don't really have to, I'm just trying to make a point. It'll be clear in just a moment, probably. So we're going to just copy down the parts where they don't change. 1 minus 2 cosine of 2x. So what happens to the angle from this step to that step? It doubles. So in the first example, my original angle was x, it became 2x, right? In this one, I have 2x. When that doubles, what does it become? 4x. So this should become plus 1/2 times 1 plus cosine of 4x dx. And I don't know if I quite closed off all my parentheses. If you're a CS person, that should bother you. Because if you don't close parentheses, then you're in trouble, right? Yeah. I know, all sorts of things. I won't dock you for that on quizzes and tests, but just it probably is good to be careful. All right, and I'm going to do, before I integrate, I'm going to do one more thing. It's always easiest to combine like terms before you take an antiderivative, right? So let's distribute this 1/2. And then there you can add some constants together. You could add the 1 and the 1/2 you'll have once you distribute that 1/2, right? So what's 1 plus 1/2 going to be? 3/2. Great. So 3/2 minus 2 cosine of 2x plus 1/2 cosine of 4x. And it's a teensy bit tedious, but now you can get it, right? So what's the antiderivative of 3/2? 3/2 x. Does that help a little bit? So 3/2 x. Okay. This one's going to be, it'd be 2 sine 2x over 2, and the 2's will cancel, right? So I'll put the 2 over 2 there, but I'm just not going to write it over, because I'm going to need to go to the next example. What's the antiderivative of the cosine 4x going to be? So it'll be 1/2 times 1/4 sine of 4x plus c. And you can choose to or not to distribute the 1/4. I think if the directions say to distribute, you should distribute the 1/4 and multiply and stuff. But for now, I think we should just move on to the next problem. Oh boy. Oh boy. Well, actually, you guys can do this one, without my help, really. So what do you think the first step is? Distribute, expand, right? Do 2 plus sine x, 2 plus sine theta times itself. Just do that and see if you can figure it out from there. Yeah?
Can we go back to that?
Oh, no, not a problem. Yeah, so I'm just going to pause my recording, take your steps against mine as you're going, okay? And I'll show more work than I usually would, just so you can see if you made any errors and see why. Say that again? Well, that too. That's not what you got? Did you get, say, 2 sine theta in the middle instead of 4 sine theta?
Yes.
Do you know why that's wrong?
Yes.
Okay.
Forgot to ask.
Yep. Also, best to have improper fractions, like, oh, this is a good thing. WebAssign will not take 4 1/2. Like, if you give it 4 1/2 in mixed number form, it doesn't know if it means 4 plus 1/2 or 4 times 1/2. Does that make sense? Because it actually is 4 plus 1/2, right? That's what that actually means. So make sure you either give it 4.5 or better yet, use an improper fraction. I do not know why elementary school harps so much on mixed numbers. Okay, I don't get it. They like act like improper fractions are the worst thing in the world when we just use them all the time. So
What are they called improper then?
I don't know.
Kindergarten teachers.
Kindergarten teachers, exactly. Well, 4th grade probably. So what is 4 plus 1/2 in improper fraction form?
9/2.
9/2. No offense to any elementary school teachers who are teaching, who are forced to listen to my lessons.
Is calculus 2 required in order to become like a 4th grade teacher?
Should be. Okay, so. Pretty sure it is in places like Finland, where education is good. Better. Oh, that one got recorded. Oh, no. That was recorded. Oh, crap. Okay. So 9/2 theta. How about the antiderivative of 4 sine theta? 4 cosine theta, right? That would be negative, yes. Good check. I was testing you again.
Just gonna put a plus and minus.
Minus 4 cosine theta, and this next one will be minus 1/4 sine of 2 theta plus c. Awesome. So far we've only done sines and cosines, right? Yes, Natalie?
Question, I didn't think I heard you, but why did you change form to
Why did this become this?
yeah, like why did form become?
Or why is this a 1/4?
4 9/2 and that's line is what she asked.
I couldn't quite hear, so tell me again, sorry.
Why did 4 turn to 9/2?
Oh, okay, great, okay, good. Okay, so, this one half distributed that 1, and then I added 4 plus 1/2. And so 4 plus 1/2 is 8/2 plus 1/2. Okay, yep, sorry, I just couldn't hear. Okay, so that kind of exhausts the possibilities for sines and cosines. Yes?
Shouldn't 1/4 sine theta be positive?
Nope. The derivative of sine is regular cosine.
Right.
Right, okay, yes. Okay, yep, great. Mm-hmm.
Were you recording when you did that little?
Of course I was. Yes, it's great. It can get me fired. Awesome. Okay, so this one, tangent's a bit different. So if you u-sub for tangent, what do you have to save to be du? Secant squared. Or if you u-sub for secant, what's the derivative of secant? Secant x tan x. Okay. So I would say if you can do this, that's the easiest way, try that first. Okay? And for you to be able to do that, notice here, I'll just show you how this one works and see if you can get the pattern. So it's tan to the 4th x, secant squared x, secant squared x. For that to work, one of them is saved. And this will have to be an even power so you can change it into tangents. Does that make sense? So can you change secant squared into tangent? It's 1 plus tangent squared, isn't it?
Yes.
I'm pretty sure that's true. Just 1 sec, okay? 1 plus, I just derived it in my head. 1 plus tan squared x. Okay, so make the substitution and go from there. You had a question, sorry?
I was just gonna say, can't you just do it where you can just make u equals tan squared x, and then du is secant fourth?
The derivative of tan squared x is not secant to the fourth x. If you had u equal tan squared x, the derivative of that is 2 tan x times secant squared x, because of chain rule. You're making up rules for derivatives that are not true.
Never mind.
Okay, but it's a reasonable thing to say, but yep, nope, sorry.
I wish I was like an omnipotent being and I could just change the rules of reality to suit me.
It's kind of like the Doctor. If you don't watch Doctor Who, you really should. Okay, after you've done your homework. So this is the integral of u to the fourth plus u to the sixth du. And let's integrate and put back in what our u is. So 1/5.
I am entirely unsure how you went from u to the fourth with that. Oh, okay, you distributed.
Yeah. Yep. So 1/5. I love it when people answer their own questions. 1/5 tangent to the fifth plus 1/7 tangent to the 7th x plus c. Yes.
If secant or tangent was an odd power, we have to do distribution.
If secant or tangent wasn't, so tangent being an odd power wouldn't affect this. Does that make sense? If the tangent were an odd power and secant were an even power, you can still do this. If the secant power is odd, you have to make this other substitution.
That's a lot.
And that's what the next example is.
No, come on.
Okay? Does that make sense? Mm-hmm. So it's okay if the tangent is odd as long as the secant is even, you can mess with this. Because then you can replace the other remaining even secants by tangents. But if the secant is odd, then you'll have to mess with the other substitution. And occasionally both substitutions work. Like the example we'll do tomorrow, we can do it 2 different ways, and I'll show you both ways. Okay, so let's try one of. So tan to the 5th secant squared. So the reason the previous method won't work on this one, so if we tried to let u equal tangent, and du is then secant squared x dx, you see how we have a single secant left over? And we don't have anything to replace that with. Okay, so that's a no-go. We know from it for secant squared, right? Okay, so then this substitution, not gonna work. So your other option is to try to let u equal secant. So you have to know the derivative of secant. You can't have forgot that from Calc 1. It is secant x tan x. Very good. So you're going to save a secant and save a tangent. So break it up. That's now tangent to the 4th x, secant squared x, and you've got a secant x and a tan x that are being reserved to be the du in your substitution. Yeah.
Would you say it was like a good rule to remember that which one's even when you take it out? Or?
Your book actually has rules. Like if you go after doing this lesson, if you go and look at them, it tells you like a good like rule of thumb for everything. So I would go take a look at that. It's not like I don't want to answer, but if the secant power is even, you can let u be tangent. If the secant power is odd, there might be an additional requirement that I'm going to mess up if I say it without looking it up. Okay, does that make sense? Yeah, I don't want to mislead you. Okay, so if our goal is to let u be secant, which part of this do we have to change? The tan to the 4th. And does it make sense that tan to the 4th is tangent squared? Okay, so that's tan squared x squared, secant squared x, secant x, tan x. And so what is tan squared equal to with secants? Secant squared x minus 1 squared, secant squared x, secant x tan x. Okay. Whew. A lot of pre-processing there. now put all our u, when we put our substitution in, we're gonna get u squared minus 1 squared. Do you agree with that? Another u squared. And then what's the rest of it? Du. Woo! And then it's just a bunch of algebra before you have to differentiate, right? So first thing you have to do is expand the squared business. So what does the squared business expand into? U to the fourth minus, plus 1.
4u squared. Oh, this is not a 2 in there.
There's not a 2 in there, yep. Like I said, I love when you answer on questions. That's good. Sometimes asking them out loud just like helps you process them. Okay, so that becomes integral of u to the 6th, great, minus 2u to the 4th, plus u to the 2nd, good job. And let's anti-differentiate and plug stuff in. So 1/7 secant to the 7th. Because this is the substitution that we actually used, right? Okay. Minus 2/5 secant to the 5th plus 1/3 plus c.
How many points do you take off if you don't answer C?
Oh, I usually take off a half a point out of like, I mean, it's just, it does really matter in like applied problems. Like when you start to do like calculus in life, that plus C really does have some meaning. Especially if you like solve differential equations and stuff. So not much, okay? And chances are you're not going to forget it every single time, right? Hopefully.
Kind of.
Kind of. Okay.
Maybe we should make the penalty hard enough to learn faster.
Say that again?
Maybe we should make the penalty hard enough to learn faster.
I could do that too. I'm not going to do it. It's okay. Half point. Now, of course, you know, it's not, like these reciprocal trig functions are not things you're going to encounter like all the time. They're not as common. But we did it with, there was obviously a sine and cosine thing. There's a tangent and secant. There's also cosecant and cotangent. It's kind of similar. So your options are let u be cotangent of x or let u be cosecant of x. And which one do you choose? So if u is cotangent, what's the derivative of cotangent? Negative cosecant squared x. If your u is cosecant, what's the derivative of that?
Secant x tan x, or tan x.
Good job. Yep. Okay. Alrighty. So if you choose this first substitution, you have to save a cosecant squared. And if you save a cosecant squared, you have one cosecant left. And the problem is, you know that to change that other cosecant only involved cosecant squared. Does that make sense? It's like this one will not work. Kind of like when in the previous question, we couldn't let u be tangent. Because when we save that cosecant squared, we have a single cosecant to an odd power, and we can't change that. We know about cosecant to even powers because of the Pythagorean identities. But if you do this, what happens to the power in your cotangent? When you've saved one of them, it becomes cotangent to the fourth. And can you change the fourth power of something into second powers of cosecants? Yes, so that's the one we're going to use. So this becomes the integral of, okay, so first of all, I need a negative, right? Because of the whole negative du business. So that's going to become, oh, I didn't sub yet. So no negative yet. So sorry. My bad. Oh, it's a plus all of a sudden. The negative goes in when we substitute. I was just a step ahead of myself. Cotangent to the fourth x, cosecant squared x, cotangent x, cosecant x dx.
Wait, then what happened to the negative?
There was never, I didn't make my substitution yet. I didn't put in u yet. The negative will come up when I put in u. So which part needs to be changed, the cotangents or the cosecants? The cotangents, because they need to become cosecant to be substituted. So that would be, I think it's cosecant squared x minus 1 squared. Did I do that right? Okay. And then times cosecant squared x, cotangent x, cosecant x dx. Is that right? Okay, good. And at this stage, you make your substitution, yes? And put in the negative. So negative integral u squared minus 1 squared u squared du. It's almost the exact same as the last one, isn't it?
Yeah.
So except for, so can I just use the work from there and say that's u to the 6th minus 2u to the 4th plus u squared? I think if you guys had to actually do that, you could do it, right? The distribution and stuff. I hope so. So this will be negative 1/7 cosecant to the 7th plus 2/5 cosecant to the 5th minus 1/3 cosecant cubed x plus c. Lisa is happy. Ah, look, math, woo! Okay. All right, how about B? Yes.
Why were there sign changes?
Oh, because there was a negative out in front,
Oh,
and I just distributed it. Yep, no problem. So what do you think the B, I know, I'm sorry, there is a B. What do you think is going to be different in the B? Here we let U be cosecant. What do you think is going to happen in B? U is going to be cotangent. So let's talk about how that works. So U will be cotangent of x. What's du? Negative cosecant squared x. Okay. So you need to save a cosecant squared x. Cosecant squared x. Cotangent to the 4th x. Cosecant squared x dx. What does this cosecant squared x become? Oh, well, one of them does. It doesn't really matter, right? I'm going to change that first one into,
Plus cotangent squared.
put the negative in front of it when I make the substitution, right? Yeah, okay. So negative integral 1 plus u squared u to the 4th du. Or negative integral u to the 4th plus u to the 6th. Sorry, my u got a little funny there, my bad. And we have negative 1/5 cotangent to the 5th x minus 1/7 cotangent to the 7th x plus c.
Why is it we're always seeing those like cotangents to the 5/5 and 7ths?
Well, because you are integrating things that are to even powers, right? I mean, if you use the Pythagoreans. But this would have worked just as well if this cotangent to the 4th but cotangent to the 5th, right? That wouldn't have affected anything. Okay. The final answer, but it wouldn't have affected the fact that we could do a substitution this way. Yep, exactly. It's because the du is what determines what substitution you can make, definitely. And like I said, your book does have hard and fast, like sort of general rules that apply based on what the powers are in various functions. I think now that you've got a bunch of examples, take them and go look at those rules and see if you can figure out why they work, okay? Now just one more thing before we go. You do not have to have these memorized, okay? So no memorize. But it does allow you to take a product of a sine and a cosine, a sine and a sine, or a cosine and a cosine, and change it into a sum. And this thing is going to be significantly easier to anti-differentiate. So there are some homework problems like this. Use the notes, okay? For example, this guy, sine of 4x, cosine 5x. This is like the A, this is like the B. Using the first identity, right? I know they're super teeny, but this is the same thing as 1/2 integral sine of a minus b 4x minus 5x plus sine of a plus b, so 4x plus 5x.
Is there a reason you want to use the first identity instead of the second?
Yes, because the first one says sine times cosine, and the second says sine times sine.
Oh,
Does that make sense? Well, they're super small. That's not necessarily your fault. Why isn't there one for cosine times sine? Because you can just flip the order. It doesn't matter. Okay, great. So that's 1/2 antiderivative of sine of negative x plus sine of 9x dx, right? Is that good? Okay. So what's the antiderivative of sine of negative x? Cosine. Let's say negative. Actually, you can make it cosine x, but let me explain why. Okay, so cosine negative x. I need a negative there because of the negative on the x, right? And I need another negative there because cosine's derivative is negative sine, right? So it becomes positive in the end. Plus 1/9 sine. Oh, excuse me. Sorry. And plus is wrong, minus 1/9 cosine of 9x. Does that seem good? Okay, and here's something else you can do. What kind of function is cosine, even or odd? Think about its picture. Cosine does this, right? That's an even function. So cosine of negative x equals just plain old cosine. Like, I wouldn't make you do that, and I think webasine won't either, but just FYI.
Will webasine take either answer?
I should, okay? Like, as in, like, if it doesn't ask me. So that's the evenness of cosine that made that happen. Yes?
Cosine negative x.
No, I use the even, because cosine is even, cosine of negative x is the same thing as cosine of x.
Oh,
Okay? And one last thing, just one small thing. I know you got classes and run out of time, but just one thing. You might run into these integration things, and you can use these formulas, and I'll tell you where they come from tomorrow. But if you get an integral of tangent, that's what its antiderivative is. Go ahead and use it. If you get an integral of secant, use what that is, and we'll talk about where they come from tomorrow, because we'll have some spare time. Okay, so just for now, if you run into that, just use it.